Let's get into it. Hi there, Chemistry 3111. This is one of the questions that we skipped, so to speak. Last class, we didn't tackle this question 18.31, which asks us, starting with benzene and using any other necessary reagents of your choice, design a synthesis of this compound. And you notice that this question is in section 18.13, which deals with nucleophilic aromatic substitution chemistry. Sometimes we call that SN, SNAR. So you can imagine that we're going to have to make this compound using SNAR chemistry, and we're going to start with benzene. But if we think about a retrosynthesis of this compound, you see that bond that I have highlighted in yellow, the bond between the carbon and the oxygen. The only way that we know how to make that bond would be to take this compound where we have a good leaving group. I'm going to put a chlorine. You could put a bromine. That's fine too. And then if we had a nitro group, para to that. Why is this the compound that I picked for my retrosynthesis? Because we know that we can do SNAR chemistry on this chlorine because we have a nitro para to it. And so all we'd have to do is take this compound and treat it with sodium hydroxide and heat. Okay, so sodium hydroxide and heat that up. And that would put our hydroxyl in this position. And then we just have to reduce this using, iron and HCl or something like that. Okay, so then the question becomes, okay, good. Well, how do I get this compound? How do I make this from benzene? So let's go back one more step, or one more retrosynthetic step, if you will. And how would I make this compound? Well, first of all, chlorine is an ortho-para director, and a nitro is a meta-director. So which one of these would I want to install first? Can anybody tell me? Would I want to install the chlorine first or the nitro first?
Chlorine.
Absolutely, right? You'd want to put the chlorine in because then if you try to do a nitration, it's going to put the nitro para to it. I agree with you 100%, Nick. So let's write down chlorobenzene. And I think that everybody knows how to make chlorobenzene. So with all that in mind, let's give it a shot. So we're going to start out with benzene. I'm just going to scooch down here a little bit. We'll start with benzene. So let's write down benzene. And first, let's start by chlorinating it. And for chlorination, we need the chlorine. We need our catalyst. So we could use aluminum chloride, or we can use iron 3 chloride, so FeCl3. And that is going to install our chlorine, which we've already discussed is an ortho-para director. Remember last class, or maybe the class before it, we looked at once you do the nitration reaction, we compared the sigma complexes that were formed if you did the nitration at the ortho or para positions compared to the meta position. And we saw that if you do the nitration in the ortho or para position, you end up with one additional resonance structure in the sigma complex. And so when we treat this with nitric acid and sulfuric acid, so we're going to start with our benzene. Try this again. We're going to install our chlorine. So we'll put that in, and we're going to do our nitration. Like this. So we need nitric acid and sulfuric acid mixed together. Of course, the chlorine activates both the ortho and para positions. However, the para is less hindered. And so we're going to assume that the nitro group is going to go into the para position. And now we're set up for our SNAR reaction. We've got our chlorine and we've got our nitro installed. Remember, the requirement is that you have, again, good leaving group. And we have a nitro group, para or ortho to it. Here it's para. And in order to do the SNAR, all we have to do is treat that compound with sodium hydroxide. And then we're going to heat that up. And then, of course, since we're in a strong base, that's going to form the phenoxide. So we need to acidify using H3O+, and that is going to give us the phenol. So let's draw the phenol. like this. So here's my phenol. So I have para-nitrophenol. And then I just want to reduce the nitro group. You could use iron or you could use zinc. Either one is totally fine. Let's choose iron just for fun. So use iron and HCl. And in the second step, since you would end up with the aniline derivative, gonna deprotonate that and treat it to a basic workup. And I mean, you wouldn't need a whole lot of sodium hydroxide here. It would just be, you know, a small amount or something so that you don't rip the proton off of here. It could be very dilute. And that would give us our desired product. Just like that. So now we have our para-amino phenol. Para-amino phenol, kind of an interesting synthesis. That one. Let's see, what was it? There was another question that we skipped, and that was this question right here. Did somebody have a question?
So I kind of did, and I think it was something that you mentioned really briefly.
Yeah.
So when doing these reactions and we have something that is ortho-para substitute, for example, we just use whatever would allow us to continue the process of creation, whether or not it would create, say, ortho or para in this instance. Like,
So
for example,
can you frame it another way, Nick?
okay, so as you mentioned in this this 18.31,
Yep.
is that chlorine would react as ortho and para substituted. So in that instance, do we just sort of move this reaction along, assuming that we have a para product, because we will, because it
Yeah.
will allow us to continue the rest of the reaction?
Yeah, and it's not just that, because you would end up with some of this compound too, right? You would also end up with a little bit of this, right? However, this is going to be a minor product.
Okay.
It's not just like, I want this product, so that's the one I'm going to write down. This is going to be minor because of the steric hindrance of the chlorine.
Okay.
Does that make some sense, right? Chlorine is in the third period. The
Yeah.
chlorine is big enough that it's going to shield, you know, or kind of block these positions a little bit. And therefore, it's going to be much more difficult for the nitration to occur ortho to the chlorine. Really, the only exception to that we've seen was toluene, right? Since the methyl group in toluene is so small that we see ortho, substitution occurring preferentially. Does that make sense?
Yeah, that makes sense. Okay.
Okay, cool. Great. Yeah, again,
Thank you.
yeah, no problem at all. Don't hesitate to stop me if you have any questions. I like answering questions about organic chemistry. Let's see. 18.35. So this is another one we skipped. Oh, this one is elimination addition reaction, right? It says, I draw the most likely mechanism for this transformation. Well, we've got bromobenzene, and we're just converting it into phenol. And you might think, okay, well, you just told me that if you have a carbon-oxygen bond on an aromatic ring, that means it's an SNAR. Well, we don't meet the requirements for an SNAR here. This reaction is not occurring, so not an SNAR. How do I know that? Because there's no electron withdrawing group, either para or ortho to it. That would be how you get an SNAR to occur, but we don't have either of those things. And so this must be elimination addition, which is what that is called. And that occurs through the benzyne intermediate. Now, luckily, there's no regioselectivity to worry about, because we tried this problem last time, 18.33, which was, took a little bit of time to solve this one, to figure out, you get two different products, okay? And this occurs by an elimination addition mechanism, but this one's a little bit simpler. I think what they're really getting at is, can you identify the mechanism? Well, again, it doesn't meet the requirements for an SNAR, and so the only other way we have to make a phenol is elimination addition. And another clue is that this reaction is done at 350 degrees Celsius. I mean, you think about how hot that is. That is really hot, to the point where it's actually difficult, I think, to run a reaction at that hot of a temperature. And so how are we going to do it? Well, we use sodium hydroxide, and you jack the temperature up enough, I guess, and you're going to end up with some phenol. So let's take a look at the mechanism here. And there's not really enough room to write out the entire thing. So I'm just going to go down here a little bit and say, okay, let's rewrite the bromobenzene, which looks like this. And what I'm going to do is my elimination is going to be demonstrated by me removing this proton. So I'm including that just for instructional purposes only. And so in the first step, my hydroxide, which is a really strong base, is going to rip off that proton. So I'll start here like this, and I'm going to make that benzyne intermediate. So let's make benzyne. And we talked about benzyne last class and said, well, we draw it this way, but it's probably more like a diradical. So now I've got my benzyne, and you can imagine this thing is really, really reactive. And so what happens is now our hydroxide is going to be able to come in as a nucleophile. So we lost our bromide, and now we have our hydroxide. So let me draw a hydroxide ion since we're in sodium hydroxide. And you could draw the curved arrow to here or to here. It doesn't matter. Okay, either way is totally fine. So let's draw it like this. And that's going to give us this intermediate. You know what? I'm going to draw it the orientation that is drawn on the slide. So why don't we do it like this? There we go. Just to be kind of consistent. Like this. So there we go. Now we've got our carbon-oxygen bond, and we have a carbanion here. So what's going to happen next? Well, remember that when the hydroxide abstracts a proton here, you form some water, the reaction mixture. And so I'm going to have some water in my reaction. And this carbanion is just going to rip a proton off of the water like this. And then we end up with our desired product. So like this. But we're not done, are we? The reaction isn't over. And if you're thinking, well, come on, here's the product, phenol, we're done. No, why is there a second step? Why does it say treat it with acid? Because since we're in a strong base, what's going to happen is that phenol is going to get deprotonated by some of the hydroxide. The equilibrium is going to lie to the side of the weaker acid, which is water. Water has a pK of 15.7, whereas phenol has a pK of 10. So in the first step, what we actually produce is phenoxide. We make the conjugate base of phenol. And then in the second step, that's the workup. So now we're on the second step. We treat that with H3O+. So let's write out some H3O+, like this. And now we're going to do the proton transfer, like that. And that gives us the desired product. That gives us our phenol. Kind of a neat mechanism. Pretty interesting chemistry, too. You know, an elimination addition. It's kind of reaction I've never done in my life. I don't think I've ever done a reaction at 350 degrees Celsius, unless it was in a microwave or something, but nothing that I can remember off the top of my head. Not that I've done everything, that's for sure, but nothing I would remember doing. So let's review. You know, students sometimes ask me, where can I find a review of all the reactions that we need to know in organic chemistry too? Well, there's no one magic bullet that I can direct you to that has every single reaction summarized. However, the end of every chapter that deals with synthesis in our textbook will always have some review of reactions. Sometimes they'll leave a couple things out, but by and large, most things will be in here. And so these are all the electrophilic aromatic substitution reactions that we looked at. And we saw how you can modify some of those groups, like we can do, you know, benzylic halogenation, we can do benzylic oxidation. We talked about the Clemmensen reaction or the Clemmensen reduction, and we talked about nitro group reduction. We actually just used that in a problem. What else? We dealt with SNAR. Again, I think I told you this last class, but those standardized exams, whether it's a school, an exam for dental school or what have you, I told you, they love to ask that question, you know. They love to ask about SNAR chemistry, so make sure you're aware of that. And the last one is the elimination addition, and that requires really forcing conditions to do. So with all that in mind, what I thought we would do is really, go ahead.
Sorry, just because I know you're going to move on. The example that we just went over, 18.35.
Yeah.
So I imagine that there are some examples in the book for these, like this specific reaction,
Mhm.
but it kind of tripped me up a little bit, so I definitely want to practice it. But I had a question. Do you think that we will be or that we'll have to approach a problem like this where another substituent is at play, or will it always just be one?
So I would definitely say that something like this is certainly within the realms of possibility. But are you talking about this one here? We have to consider the regioselectivity, or
No, because those I understand. I just want to be sure that like the reaction that we just went over, like we won't. I don't know. Maybe I'm just
because this question 18.33 is the same type of reaction. This is the exact same thing. This is elimination addition. It goes through a benzyne intermediate.
yes.
Right? But
Okay.
here we have other substituents, and so we can get regioisomers. And so yes, you would have to be able to determine, what would be the different isomers that I could, or regioisomers that I could get if you have an unsymmetrical molecule. Yes.
Okay. I'm
All
sorry.
right.
Thank
So
you.
yeah, no problem. So you might want to go back to this one and take another peek at it quickly. I spent quite a bit of time going over it in class one day, but the book might have a faster treatment. I mean, it still would be the exact same thing, but yeah.
Okay. Thank you.
Yeah, no problem at all. Yeah, no problem at all. Lindsay, I don't expect any student to remember every damn question that I ever did. That would be impossible. So yeah, it's all good. All right, well, let's take a peek at a couple synthesis problems. So we got to put our synthesis hat on for a few minutes. I picked a couple that I thought were kind of neat. I thought we'd start with something that's a little less complex. My charger just unplugged here. There we go. I thought this was kind of a neat problem. A student wrote me an email the other day and was asking me about benzylic oxidation. So I thought this would be a good opportunity to try a problem and address the whole idea of benzylic oxidation, because if you want to make this compound here, okay, well, what are our options? I mean, we're starting out with cumene, and it's got an ortho-para director on it, but you're ending up with two meta directors on the compound, right? And so, in terms of a strategy here, obviously what's doing the directing is going to be neither of these things, right? Because these are both meta directors, and you have two substituents that are ortho to each other. But again, the isopropyl group is an ortho director. Now you might think, okay, well, what do I want to do here? Do I want to put the nitro group in? Because if I tried to just take this compound and install a nitro group just with some nitric acid and sulfuric acid, that's not going to work. It won't work because, I mean, you will get nitration, but you're only going to get it in the para position. You'll only end up with this compound. So that's not good. So does anybody have an idea what kind of strategy I might want to take here? There's a couple of key steps in terms of your thought process that will lead you to the answer. Does anybody have an idea?
Could you maybe add an alcohol and then later remove it using H2SO4?
So an alcohol and remove it using H2SO4. So you mean a blocking group?
Yes.
Yeah, you could add a blocking group. And in fact, I think that's one of the key steps, okay? I think the keys are this. A blocking group is one of them, Nick, and there's one other thing. Blocking group, and that is the carboxylic acid. The only way that we know how to make a carboxylic acid is from benzylic oxidation. So benzylic oxidation, and we do have a benzylic proton here. So we can take this isopropyl group and just treat it with KMNO4 and cook it up in base and then treat it with acid, or you can just treat it with sodium dichromate. Either way, it'll make the carboxylic acid. So Nick, thank you for chiming in, because now we kind of have the answer to the entire thing, right? We know the entire answer because all we have to do is put a blocking group in first. So we're going to treat this with fuming H2SO4, which is a mixture of sulfuric acid and sulfur trioxide. That is what is going to enable us to get that nitro group where we want it. Now we've got our isopropyl. We've got our SO3H, which is our sulfonic acid. Look, this is an ortho-para director. This is a meta-director. If we nitrate, it's going there. No doubt about it. So let's put it in our nitro group with nitric acid and sulfuric acid, like that. So now we can put in our nitro group like this. All right, like that. So we got our nitro group here. We still have our sulfonic acid. So now, Nick, like you said, we're going to treat this with dilute H2SO4, and that's going to knock the blocking group off. So now we have our isopropyl still intact. We have our nitro group. And this is the key, in my opinion. You know, it's doing the benzylic oxidation. You've got a benzylic proton, and therefore you can do one of two options. If you go back to that review slide that we looked at a couple of minutes ago, the only thing that they had on there was to treat it with KMNO4, sodium hydroxide, and heat in the first step, and then in the second step, you treat that with some H3O+. However, back in chapter 17, we also learned that you could do a benzylic oxidation using sodium dichromate. So you could just put Na2, Cr2O7, sodium dichromate, sulfuric acid, and water. That will work as well. Either one is totally fine. Any questions about that one? Just two substituents, but you know, I've got to put that blocking group in there. Does everybody follow me on that one? Or maybe I'll ask you that. Does everybody just get where I went, like how to solve that one? Okay, cool. Okay, and again, don't hesitate if you have a question. So let's turn up the heat then. Turn up the juice, and let's try this one, 18.67b. I scribbled this one down somewhere in here. I thought this one was a pretty neat one because it's the same problem as before, except now you've got two carboxyl groups, right? You had this and this before, and now you throw another carboxyl group in there. So what's your, mode of attack going to be? Well, the way that I think about this is, you can do it. You're going to have to do a double benzylic oxidation. There's no way around that. You've got to do two benzylic oxidations in order to install both of those carboxyl groups. So how are we going to do it? Now, I would accept several different ways of solving this problem. This is definitely not a one possibility, can't argue with anything. I would say there's a few ways to make this compound. But what's going to be the simplest way to make this compound? So does anybody have any kind of strategy or any kind of ideas? Nick had a good one last time. Anybody have an idea? No? Okay. Well, what if we did a retrosynthesis? And what if we had this compound? What if we installed two alkyl groups? Because we know we're going to need to do a double benzylic oxidation. If I had this compound, this is 1,4, isopropyl, diisopropyl benzene. I mean, this compound is perfectly symmetrical. If I try to nitrate this thing, it wouldn't matter if I go here, 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 here. It all gives you the same product. So all I'd have to do is nitrate this thing and then just do a double benzylic oxidation, and I'm done. So then the question becomes not much simpler, but simpler. It kind of becomes, well, how do you go from benzene to here? Well, how do you install an isopropyl group? You do Friedel-Crafts chemistry. So let's install an isopropyl group. What do we need to do? We need to treat it with isopropyl chloride and aluminum chloride, like this. And we know that there are limitations to Friedel-Crafts chemistry, isn't there? But we can do a Friedel-Crafts with an alkyl group present. So let's do another Friedel-Crafts. So that's kind of an ugly looking isopropyl chloride. There we go. That's a little better. So there's our Lewis acid. And now we have this 1,4-diisopropyl benzene. This. All right. And what are we going to do next? We're just going to nitrate it. So nitric acid and sulfuric acid are conditions to make our nitronium ion. And then it doesn't matter about ortho-para director. That's neither here nor there, really, because there's only one type of position available. And so we're only going to end up with one possible molecule. Let me try to draw this bond a little straighter. There we go. There's our nitro. And now we just do our benzylic oxidation. I'm going to use the conditions that the book seems to favor, which is potassium permanganate, sodium hydroxide. We heat that up. Of course, that gives you a carboxylate. So in the second step, you have to treat that with H3O+. Let's see, what else did I have here on the old hip parade?
Mr. Dion,
Yeah, go ahead.
is there a reason that you use two isopropyl groups instead of some other, like just a methyl or some other kind of alcohol?
You could, absolutely. You could use a methyl and a methyl, no problem. Yep. You know what, Caitlin? I looked at my old notes and I had used an isopropyl and a methyl. So
Oh, okay.
I used one of each. You know, Caitlin, as long as you have, you know, the only flaw that I could think of that a student might do or an instructor is pick a tert-butyl group, right? Because if you picked a tert-butyl group, then you can't do a benzylic oxidation, you're toast, right? Absolutely. So you could put an ethyl, you can put them, I don't care. Just, yeah. Does that answer the question?
Yes.
Okay, cool. Great question. Another one that I like making tetra-substituted compounds. They're pretty cool. So this one here, this is 18.67E. I like questions where you get a whole holy host of things to add to the molecule. So here we're starting with benzene. We've got nitros. We've got carboxylic acids. We've got bromine. Is there anything here that your eye is drawn to right away? I'm sure you might have, some of you probably tried, if not all of you, probably tried this problem over the weekend. You know, there's one thing in this compound that my eye is drawn to immediately, and it's this guy, the chlorine. Why? I know that I'm going to put this in last because this is an ortho-para director, this is a meta-director, and this is a meta-director. And so everything that's not circled, the bromine, the nitro, the carboxyl group, they're all directing to that position. So I've just got to put the chlorine in last. So that means that I've got to make this compound where I have my carboxyl group, I've got my nitro group, and I've got my bromine. The only way I know how to make a carboxyl group is from a benzylic oxidation. And the only way I know to do a nitro is from a nitration. And I'm going to have to install the nitro the last out of all these three groups because I can't add an alkyl group if I have a nitro on my compound, right? Because Friedel-Crafts, because I need to do Friedel-Crafts before I make the carboxyl group. And I can't do a Friedel-Crafts if I have a nitro on the ring. So that tells me, in terms of retrosynthesis, again, I'm going to want to make this compound. And Caitlin, you could make para-bromotoluene. You could make, you know, para-bromoethylbenzene. You could make para-bromocumene. I don't care. As long as you have a benzylic hydrogen in there. That's all that matters. So now the question becomes much less complex. And I think, you know, actually, I misspoke. I made a mistake in what I just said. You can't use toluene. Here, you'd have to have an isopropyl or an ethyl because if you use toluene, you'd get bromination here or more of it. So we'd want to put that isopropyl group in there, I think. Now, you want to get as much para product as possible. So let's start with our isopropyl chloride and aluminum chloride. That puts in the isopropyl group. Comme ça, as we say in French. And next we want to install the bromine. So we're going to use bromine and iron 3 bromide. Iron 3 bromide, like that. Now we've got our bromine in the para position. And again, I think that this isopropyl is a great choice because you've got a benzylic proton to make your carboxyl group. And it's so big and bulky, right? You've got free rotation here. It's going to direct that bromine here. You're going to get mostly the parabromination product. Next, we can install our nitro group because we've got No, sorry, we want to do the carboxylation first, don't we? Yes, we do, because if we make the carboxyl group first, then we'll have a meta director and an ortho director, so we'll be directing to that carbon. So let's do the oxidation first. You know what? Jones oxidation doesn't get enough love, so let's use sodium dichromate, sulfuric acid, and water. And that's going to give us parabromobenzoic acid, this compound here. Now we've got a meta director here, and we've got an ortho director here. And so both of these are going to direct to this position. Now we can do our nitration. I'm running out of space here, aren't I? So we'll do our nitration, nitric acid, sulfuric acid, mixed together. Good times for all. Right? Nothing like working with a mixture of dangerous acids. So now we have our nitro group installed. And this is kind of where I wanted to get to, because everything on this ring is directing to this position that I have highlighted in yellow. So now we just need to do a chlorination, and we are done. So let's install the chlorine. Let's use chlorine. Let's use some FeCl3. And there you go. You know, tetrasubstituted compounds, they look really complicated, and they certainly aren't simple. But if you take it kind of stepwise, some of them are not too bad. There we go. I mean, how many total steps are we dealing with here? Let's count them. We've got, let's see, 1, 2, 3, 4. Actually, that's not all that bad. Let's see. There was another one I wanted to try with you, which was... Oh, I wanted to try something that involves SNAR in a little nuance. It was 18.67F. So let's see here, 18.67F. I thought this was a good one. You're starting it with benzene, and you want to make, this compound where we have an ethoxy group on our molecule. So we're going to have an ethoxy group like this, and then we're going to have a nitro group here, and then we've got a chlorine pair to it, like that. Okay, so I noticed that I've got a carbon-oxygen bond between a carbon in the aromatic ring and this oxygen. So I've got two possibilities: elimination addition or SNAR chemistry. Could anybody give me a vote here or suggest which one would be better? Would it be SNAR chemistry or elimination addition based on the molecule, the final product? Based on the final product, what do you think would be a better choice? Anybody have an idea on that one? Notice that we have a nitro group that's, sorry, go ahead.
SNAR.
100%. Absolutely, right? How did you know that, Karen? Because we have that nitro group that's para to that carbon-oxygen bond. So if we can get that nitro group in there with a chlorine or a bromine paired to that, we're good to go. And just the fact that we want to put this chlorine in, I mean, we've got an ortho para director here and we've got a meta director here. Both of those groups are directing to this position. And so just taking one step back, just one step, we would want to do this. We just want to have the ethoxy group and the nitro group. And again, they're both directing to this position. Here's my yellow highlighter. They're both directing here. And so all we'd have to do is a chlorination. So then the question becomes, okay, well, how do I get from here to here? Well, again, we're going to have to use SNAR chemistry. So we're going to take the same approach that we did in one of the questions, the first question we did today, actually, where we first made chlorobenzene and then we installed the nitro. So what I wanted to show you is a really interesting nuance here. That, I don't know if nuance is the right word, but let's just get started here. So first we're going to put in our chlorine, which will eventually be our leaving group. And then we're going to install our nitro group. So let's treat that with nitric acid and sulfuric acid. like that. Let's put our nitro group in. And now we're set up for our 4-hour SNAR chemistry, right? What was the requirement? You've got to have a nitro group, something is strongly electron withdrawing, and then you've got to have a leaving group, either ortho or para to it. So we're ready. Now, here's the thing. If I ask my students, and there's nothing wrong with this, okay? Just hold on a second. You know, students will say, okay, well, why don't I just treat this with sodium hydroxide and heat? That makes the phenoxide. Then I treat it with aqueous acid, and that's going to give me para nitrophenol. And then after that, I can just do a Williamson. The Williamson, which is to treat it in the first step with sodium hydride, and then the second step, you treat it with ethyl iodide. And that would give you this compound. So now you've got your ethyl group on there, you've got your nitro, and then the last step is just going to be chlorination. So Cl2, AlCl3. There is nothing wrong with this synthesis at all. I would give this 100%, no debate. It's perfect. There's nothing wrong with it. However, there is a faster way. There's a little bit of a quicker way. I'll show you what it is. It's to get from here to here. And I haven't looked at the solutions manual, so I'm not exactly sure how he does it. I could try to find it, but I don't know where my solutions manual is. So I don't know. It's somewhere on my computer. Anyhow, that's neither here nor there. Where the hell was I? So there is kind of a shortcut to get from here to here. Does anybody know what it is? Or I have the blue air. Yeah.
I think I saw it in the book. I'm not sure. I can't like fully remember. But is it NaOET?
Yeah, absolutely. You know what? What question is this? Is this F? No, what question? I don't even know what question I'm on here. Yeah, it is F. Okay, I found my solutions manual. And yeah, so he does it this way. Yes. So what he does is just treat it with sodium ethoxide and heats it up. Why can you do that? Because ethoxide is a dandy nucleophile. I mean, that's going to do an SNAR like stink on this thing. And that gets you all the way over to here. I mean, you know, it gets you all the way over to here. So you kind of skip a couple of steps. You don't have to do all this sodium hydroxide, acidify, rip off the proton, treat it with iodoethane. This, I would say, is a shortcut. And let's put here, shortcut and in the book. Okay, so there's nothing wrong with what he's doing. It's perfectly reasonable. And you got to remember that organic chemists are people who like to get the maximum amount of work done for the minimum amount of effort. And so if you solve it this way, I'd say it's perfect. There's nothing wrong with it. But if you solve it this way, where it's a few more steps, I'd give that 100% too. I don't see any problem. I think you should understand both routes. Does everybody see what's going on here? Or just, could you give me a thumbs up if you follow me, or stop me if you have a question about it? Okay, cool. Yeah, and what you'll find is that if you read through this solutions manual, as the course progresses through the next couple of chapters, he'll do more and more of this stuff where he's like, well, you're supposed to know that ethoxide is a good nucleophile too. So let me just whip this little shortcut in front of you, you know? He'll do these kind of little tricks, not a lot, but once in a while. And I think it's kind of neat, you know, to kind of show students, you know, there's more than one way to skin a cat, so to speak. All right, there was one other one I wanted to look at. Oh, yeah. Let's look at one more. It's not a super complicated problem, and everything's complicated in organic chemistry, I know. But it's this question here, which I was looking at it last night, and my eye was drawn to it. This thing here, because I don't think it's abundantly clear. You look at the molecule, at least it wouldn't have been to me when I was a student. How in the hell, pardon my language, how would you make this thing? You've got an orthopara director here, and then you've got an orthopara director here. They're meta to each other, and there ain't a nitro group in sight. So, you know, we think about everything that we've looked at today. It usually involves a nitro group when we're talking about meta substitution. Did anybody try this one over the weekend? Or has anybody looked at this and just figured out a solution? Because you have to dig back You have to go back to chapter 16 to solve this thing, which is, you know, this is like where organic chemistry rears its ugly head, and that, you know, we expect you to be able to remember old reactions. Anyhow, let me just show you how to do this one in the interest of time. Here's the key step. It's recognizing that in order to make that tertiary alcohol, this guy right here, what you would want to do is have a methyl ketone or an acetyl group there, okay? And what you would do is you would take this ketone and you would treat it with methyl magnesium bromide, so methyl Grignard, and then you would acidify that, and that would give you a tertiary alcohol. Now I think it probably makes sense to everybody, but this, I would say, this is the key step, really, in my opinion. You know, maybe somebody else has a difficulty remember something else. But here we've got a meta director, and here we have an ortho-para director. So obviously we have to put this group in first, which we can do by Friedel-Crafts Isolation. Then we can install the bromine in the meta position. Then we can do the Grignard. So there's not even a blocking group or anything like that to worry about, but it's being able to look at this tertiary alcohol and say, well, I could make it from this acetyl group. This is where practice really comes in handy of getting used to seeing stuff and really thinking about knowing, you know, do I understand this reaction fully? So let's write a solution, get a little practice on our Friedel-Crafts isolation. So if we want to install a carbonyl with a methyl, here's our carbonyl with a methyl, and then we need a chlorine. So this is called an acid chloride. We use our Lewis acid catalyst. We make our acylium, which undergoes electrophilic aromatic substitution. Then we restore the aromaticity. And so we end up with this compound. This is called acetoacetophenone. I asked you to remember the name of this compound, I think back in chapter 17. It's a very common organic compound. People will use it for a starting material in synthesis sometimes. And it's going to come up in today's lecture, I think, from chapter 19. And this is a meta director. And so now we can install that bromine, Br2 and FeBr3 in the meta position, like this. There we have it. And then the last couple of steps are just going to be some Grignard chemistry. One, methyl magnesium bromide or methyl Grignard. And the second step is going to be treated with some aqueous acid, or if you just want to write H2O, that's fine. That's how he did it in the old version of the textbook, and that would give you the product. Okay, are there any questions from chapter 18 or any questions from the textbook? And of course, if you're running over one and you can't figure it out or you have a question, you can always email me about it. Any other chapter 18 questions? Another one, just in the interest of time, I want to move on to chapter 19, but there was another one that I thought I would draw your attention to. And I'm sure that most people have done these ones already, but I want you to also take a look at questions like 18.63A and B. I mean, these are ones that I asked that involve strong activators, you know, like a methoxy group or something, because those, you know, we said can do polybromination, but we assume that they don't. So anyhow, that would be something else you might want to take a look at. Okay.